Okay, so what I gave you as a motivating example last time was kind of a toy example. I gave you the challenge of how do I do a countdown, go from 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, blast off, and if I lived in a world where I could not write loops. No for loops, no while loops, no do while loops. Instead, all you can use are functions, and of course you can't just hard code everything. And that's actually not an artificial world. There are plenty of programming languages out there where using recursion without loops, they either completely discourage the use of loops or they make it absolutely impossible by not building them into the language at all. Those are mostly functional programming languages, and as their name suggests, they are function-based. Every operation is done through some sort of a function call or a function return value. As a matter of course, if you're going to work in those functional programming languages, then yeah, you're going to have to use recursion. But what I'm going to show you by the end of the day is that in a programming language like C, you don't want to use recursion for some very, very good reasons out there. So what I'm going to do instead is instead of harping on recursion, is I'm going to show you how to avoid it. Okay? But before we do that, we need to understand what is recursion and why might it be bad in certain cases. For that, I'm just going to go ahead and go to Google. I usually use DuckDuckGo now, but DuckDuckGo does not do this joke. Only Google does. Let's go ahead and see what recursion is. Oh, I misspelled it. Do you remain recursion? Do you remain recursion? Do you get it? That the idea is that it's self-referential. You might have seen pictures of, like, say, the Mandelbrot set or something like that. Let's go ahead and use Google image search now for Mandelbrot set, right? There we go. And let's just pull up some images. So these are fractals. Fractals are self-similar objects. They are defined recursively. Or the Sierpinski triangle. Sierpinski triangle. There we go. That you form this by simply cutting out the middle triangle, and then you recursively do that. This triangle up here, you cut out the middle triangle. Then you recurse on the 3 other triangles. You cut out the middle triangle, and you go down infinitely so. So an example of recursion is fractals, and they do have actual mathematical applications, and they do actually have engineering applications too. If you rip open your phone and look at what a typical antenna looks like, it'll look like kind of like a fractal. It's not an infinite fractal, obviously, but a fractal kind of like shape is how you can actually optimize the signal strength and reception. So these things do have applications. Another example that is always trot out in any computer science 1 or introduction to recursion, and the example that's always trot out is the Fibonacci sequence. That if it's defined as an infinite sequence, that if you start out at 0, well, then it's 1, then the next one is 1, and otherwise it is the sum of the 2 previous values in the sequence. So you can see that 1, 1, well, what's the next one? It's the sum of the previous 2, 1 plus 1. What's the next one? It's the sum of 2 plus 1, that gives you 3. What's the next one? It's 5 because it's 2 plus 3, or 3 plus 2, right? And so you keep going, you see that 89 is the sum of 34 and 55. What would the next value in the sequence be? 55 plus 89? 144? Is that right? Okay, whatever it is, right? Yeah, 144, I think. I have to convince myself of the math, but yeah. That is the, now I hate this example and I love it at the same time. I hate this example because every time I see a coverage of recursion, this is always the first go-to example. If you look up recursion, if you look up how to do recursion in language X, this is always the example that's given. It's a terrible example in that why would you ever actually want to compute this? This is not a practical example. Nobody is computing, nobody's in industry is computing Fibonacci sequences all day. So why it doesn't motivate why you would want to use recursion or why you would not want to use recursion. Actually, it does. That's why I also love this example, because it shows you exactly why you should not use recursion, and we'll understand that in a second here. Okay? But before we do, let's go ahead and review what we did last time. This is the countdown function that we made, and at this point, I only did this so that the math would render. Now I'll go back to Markdown here. Increase the size. There we go. So there's the countdown function that we used last time. And the idea was that we go into this function, and if we've already reached the end of the countdown, we've already reached 0, then we'll go ahead and print blast off and then return, right? Implicitly, there's a return statement here. Return. Otherwise, if n is strictly greater than 0, we've not reached our countdown yet, right? We started at 10 or 9 or 8, or we're on 8, whatever. So what we're going to do is we're going to print it out, print out 10, print out 9, whatever value we get into this function. And then we're going to call the function again, countdown, but we're going to decrement n so that we're making progress towards that last number 0. If you actually run this like we did last time, then it counts down 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. But when it hits 0, then it hits blast off. Right? So there are, in the context of coding, right? In the context of coding, recursion simply means when a function makes one or more calls to itself. Right? Context, I'll fix that. There we go. Right? And that's what we mean by recursion with respect to coding. It's just simply a function that calls itself. By the way, not all programming languages have supported recursion. The very, very early versions of either COBOL or Fortran, I forget which one, did not support recursion. You do not have to use recursion in most programming languages. The only programming languages where you have to use recursion are where they do not give you any means of doing loops. Right? So that's our motivating example here. Let's go ahead and try to identify some of the parts of a recursive function. So parts of recursion. All right. So first of all, every recursive function needs at least one base case. Right? A case in which no recursive calls are made. Why do you think that you would need that? Think of the blast off situation here. What if I didn't have that base case up here? What if it just kept going? 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, -1, -2, -3. You just keep going on forever. If you didn't have this, you'd have infinite recursion. And if you have infinite recursion, where a function is calling function is calling function is calling function, what am I doing? I'm adding stack frames to the stack. Eventually, I run out of stack space and I have a stack overflow. That's one of the reasons that you don't want to use recursion, or that I'm going to try to argue that you should not use recursion, is because you are abusing the stack space instead of local variables. Right? The base case is where you make no recursive calls, and also each recursive call, function call, should make progress towards the base case. If you're not making progress towards the base case, for example, in my countdown, instead of going n minus 1, what if I just did n? And now countdown of 10, countdown of 10, countdown of 10, countdown of 10. Again, if I'm not making progress towards that base case, then I'm in an infinite recursion. Man, these two things sound really, really familiar to me. A base case in which you stop, and making progress towards that base case. What is that? A loop, right? A loop has an initialization, right, where you start the loop. You want to make progress towards your terminating condition rather than the base case. So basically, recursion is nothing more than a loop that's exploiting the stack space instead of exploiting a local index variable of some sort, right? Everybody in here could rewrite this entire piece of code here to just a for loop. For int I equals 10, I is less than or greater than or equal to 1, I plus minus minus, so you're decrementing. Print I, and then after the loop is done, that's where you print blast off. Right? You could do this with just a regular old loop. You don't have to use recursion. Also, corner cases may need to be handled separately. Right? This is basic error handling. For example, what if I started my countdown below 0 already? What if I started my countdown instead of at 10, I started counting down at -10? Right? Well, will my base case ever actually occur? Will I ever reach my base case? No, I've overshot it already. So I'm going to, again, have infinite recursion. Right? So corner cases may need to be handled separately. For example, you have a check at the beginning. If you start your countdown at greater than 0, then we'll go ahead and count down for you. But if you start your countdown at negative or less than or equal to 0, maybe we'll just print and blast off right away. Right? If it's equal to 0, otherwise you can add another case here where you reject it as bad input or something. And that would be another base case. So you don't have to have just one base case. You can have many base cases. For example, the Fibonacci sequence here has 2 base cases. When n is 0, when n is 1. You would end up returning 1. Right? So those are the basic parts of recursion. A recursive function simply makes progress towards, it makes a one or more recursive calls to itself. So recursion, good? I don't know. Recursion can be a useful, I'll put useful in quotation marks here, and good tool. For example, many divide and conquer algorithms rely or are usually presented as recursive. And in fact, that's why I still cover recursion in this course, because the very next topic that we're going to start next week is searching and sorting. Some very general algorithms that we're going to be looking at are binary search, linear search, and sorting algorithms like quicksort. They all take a divide and conquer kind of approach. Just as a preview here, if you want to sort an array, let's go ahead and split that up or that array up into 2 pieces. We'll go ahead and sort this array over here, and then we'll sort this array over here. Then what we can do is, this is an algorithm called merge sort. What we can do is we can take these 2 sorted arrays and then merge them together by interleaving the elements. Right? Well, how did these get sorted anyway? I don't know. What I'll do is I'll recurse on them. Now I've got an array. If I started out with an array of size 16, now I've got an array of size 8. And now I only have to worry about sorting 8 things. I don't know how to do that. So I will recurse until I get down to 4 things. Recurse until you get down to 2 things. Recurse until you get down to 1 thing. How do I sort now? 1 thing. By definition, it's sorted. Right? So divide and conquer strategy. Split things up into 2 things and 2 sub-problems, and go ahead and take care of each one of those sub-problems separately. And then on the way back up, merge them somehow. And that's actually pretty easy. So divide and conquer algorithms are basically recursive algorithms. They're usually presented as recursive algorithms. Many functional programming languages require recursion or highly discourage the use of loops. Right? These are functional programming languages like Pascal or Scheme or things like that, where it's a completely different paradigm. So I've kind of mentioned, and we will look at in 156 next semester, object-oriented programming. That's a completely different paradigm than structured programming. C is a structured or imperative programming language, meaning that you do A, then B, then C. You read a program like you read and write a program like you would like a paper, right? You maybe make a function call, and state is changed through a function call. With a functional programming language, though, it's a completely different paradigm. Imagine a world where you don't have loops. Imagine a world where you do not have variables. Right? Instead, everything has to be communicated through either parameters or return values. Right? That's a purely mathematical idea of how to program. And if your mind works like that and thinks like a mathematician all the time, where you're just applying functions and category theory and stuff like that, great for you. But the vast majority of people don't think like that. They think like they write. They write top to bottom, left to right, and they write in an imperative style, in a structured programming language style, because that's the way we think. Right? But it is important to learn about it, because eventually you might have to experiment with a little bit of functional programming style. And many other programming languages have adopted functional aspects. For example, lambda functions, where you don't have a function, you just have this expression, inline expression. That's a functional programming style that has been adopted by many languages. But is recursion bad? I don't know. Actually, let me go back over here, and let me go ahead and add one more thing to the good. Recursion can lead to simple, clean code that is easily understood. Right? All right, well, this last point here, recursion can lead to simple, clean code that can be easily understood. What I'm going to do is I'm going to add yet another adjective to that. Beautiful. Right? So what is it about beauty? What do we say about beauty? It is in the eye of the beholder. Simple, clean, beautiful. These are subjective terms, right? Whether or not you like recursion, I personally don't like recursion, but that's my opinion. That's a subjective thing. If people love recursion, okay, that's their opinion. It's a subjective thing. But what about the bad? Those are things that are objective that you can actually measure. Recursive functions risk, recursive functions essentially abuse the stack space. Right? So instead of creating local variables where int I is equal to 10, I minus your countdown, where you're just using one variable, you are abusing the stack space by creating 10 different stack frames to count down from 10. Each one of those stack frames has its own value of n. You've exploded the amount of memory that you need to use to actually do this. And you've risked stack overflow. Risks stack overflow for what are called deep recursions. Right? Now, most recursions are going to be shallow. But if what I'm going to show, we're going to develop an example here in a second that can end up being very, very deep and can end up being killing the stack space almost immediately. Right? In general, recursion is not needed. Right? Any recursive function. Now, I'll put an asterisk on that. There are recursive functions in mathematics that cannot be computed iteratively. They're non-computable recursive functions. We're not going to talk about those because we're doing computers. Anything that we write, by definition, is computable. Right? So any recursive function can be rewritten as a non-recursive function using a loop or a stack. In other words, like your call stack, etc. Right? You don't need to do that. You can always rethink what you're doing. Recursion can often be simulated, right, using an in-memory stack on the heap instead of abusing your very limited stack space on the program stack. Some organizations even ban recursion or the use of recursion. For example, NASA. Right? Why do you think NASA would want to ban something that's risky like this? Something that abuses the stack space, something that is not going applications like embedded systems on satellites, on highly expensive, very, very expensive equipment. You do not want to abuse the stack space because you don't even have that much stack space. So they ban recursion outright in their style guides. I wish I could find it again, but I've seemed to have lost it. Recursion also risks needlessly recomputing values over and over and over. And we're going to see an example of that today as well. But before we do, let's go ahead and take what we've talked about so far, the parts of recursion, and let's take that countdown example, and let's make it actually useful. Again, I said that this is a toy example, but you can actually make it useful and do something with it. So let me go ahead and get rid of the Sierpinski triangles there. Let's go ahead and write a program. That's too big. Let's write a program to sum up the values in this array, right? But we will do it in a world where we do not have any loops. Right? In other words, anybody who's actually going to do this in practice would just have a for int I equals 0, I is less than n, I plus plus, dot, 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 blah, 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 right? You'd end up doing that. But let's go ahead and live in a world terrible, terrible world in which loops do not exist, right? Or we can't afford one or something, right? So I'm going to create a function to do this for me. I'll just call it sum, okay? It's going to want to return the total, so I'll go ahead and make its return type int, right? What do I need to give to this function, though, in order to sum up the elements in this array? Well, first of all, I'm going to need to give it the array, right? Const int star arr. And also, what else do we need to do in the C if we're going to pass in an array? A size, int n. We might need to pass something else in. So what I want to do is I want to first think about those two elements. The base case, where do you stop? And the non-base case, the recursive case, where you make another recursive call. So if you think about that for loop that I was about to write, but we can't afford it, where do you start? Where do you stop? So where do you stop? Well, I'm adding the first one, 2 plus 3 plus 5 plus 7 plus 11 plus 13. That's where I stop, right? If something is equal to n minus 1, that's where I stop and return what? Return something. I don't know. We're developing this as we go along. So this something, that's something that's going to have to be communicated to the function, just like we communicated n up here. Now it's a different n. But what we were doing up here is what we were passing that counter variable. Right? So I'm going to do the same thing over here, but with another variable called I. Right? And so if I is equal to that, I've reached the end of the array. All right? And I only need to return what? I've reached the end. I just need to return that element. Array sub I. I'm returning the last element. So the way that you think about this is I'm going to recurse on 2, recurse, 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 recurse. I'm just doing a loop here. And when I get down to the end of this array, I'm simply going to return 13. And on my way back up the recursion, think about recursion downward. You're recursing on the first element, then the second element, then the third, the fourth, the fifth, the sixth. When you get down to the sixth element, we'll return that element back up to the calling function. That calling function will take this and add it to its element, all the way back up. Right? So the way that we're going to do that is, again, through recursion. Else, return the array sub I, my current element, plus sum of array n and I plus 1. Right? I am abusing the stack space here in order to get away with not having a for loop. Instead of for I equals 0, I is less than n, I plus plus, I am doing that here in the function parameters instead. Right? I plus plus, I plus 1. Right? Okay. I'm going to return my element plus whatever recursive call, whatever recursive call it gets added on the way up. Right? All right, that's pretty good. Now let's go ahead and go over here and int total is equal to sum. How do I get things kicked off? Again, this is just a loop. Recursion is nothing more than loops. So what I've got here is my base case. That's my termination condition. I've got my continuation here, right, where I go I plus plus, right, implicitly. How do I get things kicked off? What do I pass into sum? Well, the array and the size. Where do I start I? Where do you start it in a regular loop? 0. Right? And then let's print that out. Print f %d and the line total. There we go. Let's run it. And I don't know, is it 41? 5, 10, 17, 27, 28, and 41. Yep. All right. Convinced myself of that math at least. All right. So how would you visualize this? Let me go ahead and pull up that Python tutor. Nope. That Python, it's Python tutor, but it has visualizations for many programming languages. And let's go ahead and visualize its execution. And we will see it abusing the stack space in practice right here. Right? As we go along, come on. There we go. So next, next, next. There's my stack. All right, there's the sum function. Right? There's the sum function. Copies of everything. Copies of the pointer to the array. Copies of the size of the array. And different variables in different stack frames for each value of I. Right? Fast forward here. Wow. Now, the recursion is going down here. 1, 2, 3, 4, 5, 6. OK, there. It's finally done with its recursion. What is it going to do on the way back up? Right? That was popped off the top, and a total was returned. Keep going, pop off the top, popped off the top, popped off the top, popped off the top, until we finally get back to the calling function, at which point it prints 41. So instead of having one variable, right, and not having to deal with, and just incrementing it directly in a for loop, we've abused the stack space here. It's not that big of a deal for an array of size 6. If it's an array of size 10,000, so if it's an array of size 1 million, that's not happening. Right? Why? 1 million stack frames. Right? If each one is even only 4 bytes, that exceeds the stack space of even on CSE. Right? So you are abusing the stack space. You don't want to do that. Right? So how do you get past that? Eliminating recursion. Right? In general, you can, again, like I said before, always rewrite a recursive function. Right? Well, how would we end up rewriting this function right here, by the way? That's how you learned it to begin with. Right? Just a simple for loop. Right? What about, and at this point I'm going to get rid of REPL, and let's do a real programming language environment here. What about that Fibonacci sequence? Right? So let me go all the way back up here. And unfortunately, you can't see the math, but let me go ahead and make it so that you can see the math. There we go. It's nice and mathematical there. Right? We're going to we're going to write a function to compute the Fibonacci sequence. But I'm going to do it with a twist to show you why this is so bad. All right? So first of all, let's go ahead and write that function. I'm going to go ahead and use a long instead of an int. A long is much, much larger. It's a 64-bit integer. So it can, because the Fibonacci sequence grows exponentially. So it's going to get very big very quickly. Right? I'll call it recursive fib short for Fibonacci. Right? And we're going to take in a value n. Right? And this is where the simple comes in. If you've got something like this where it's recursively defined, hey, there's a base case, there's the recursion. All I need to do is cut and paste my math into my code. Right? If n is 0 or n is 1, then I'll return, what was the value? 1. Right? Now some authors start the Fibonacci sequence at 0, then 1, and then 0 plus 1 is 1. We're just skipping that and going all the way to 1. Else, return a call to recursive Fibonacci on, again, n minus 1, and a recursive call to Fibonacci on n minus 2. N minus 1 plus recursive Fibonacci of n minus 2. There we go. All right. Now here's the twist that I'm going to throw in. I want to know how many function calls am I actually doing here. Num func calls. Right? And what I'm going to do is, the very first thing that I'm going to do, even before I do my base case here, is I'm going to go ahead and increment this guy so that I can report how many function calls did you actually make to compute, say, the 10th Fibonacci number or something. Right? We'll take this in as a command line argument. Int x is equal to recursive fib. Let's go ahead and compute the 10th Fibonacci number, which should not be that bad. It should not be that big. Right? Printf fib of, we take that in as a command line argument. So %d is equal to %lu, I think ld, for a long integer. Right? And number of calls, %ld, we'll print that out as well. So we've got n, x, and number of num function calls. Okay. Let's go ahead and compile this. Why? But the argument is of type int, is it? Oh, sorry. Int x. I meant long x. There we go. All right, there we go. Now let's go ahead and run it for the 10th Fibonacci number, which is what I already had over here. 89. This is the 10th one. This is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Just testing this to make sure that it works. Well, what's the 11th one? What should that be? 144, I think we said. I was right before. Yay. What should the 12th one be? Well, it'd be 89 plus 144, so 220, 233. Yay, it works. But do you see something else there? Each time I go up, how are the number of function calls growing? Not that bad there. Now 3,000, right? So if the Fibonacci sequence is growing exponentially, then let me go ahead and go with just 20. If the Fibonacci sequence is growing exponentially, then how is the number of calls growing? Also exponentially. Right? In fact, let's go ahead and let's see if we can compute this 100. Right? What's the 100th Fibonacci number? While we're waiting for that, let's make sure that I have the right answer. So Wolfram alpha, 100th Fibonacci number. All right, so when we finally get an answer back, it should be like that, 3, 4, 5, and blah, 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 right? How long should I wait? 2 months. 2 months? Okay. Try 100 trillion years or so, literally. Right? You can go ahead and compute this out. The Fibonacci sequence grows exponentially according to with a base of the golden ratio, 1.6 something, something, something. We'll just go ahead and round that up to 2. What the hell? 2 to the 100. How big is that? Even if I'm able to do a billion function calls per second, you're talking about not centuries, but millennia. Right? Let's go back to Wolfram alpha here. We'll just do a hand-wavy calculation here. 2 to the 100 divided by 1 billion operations per second. So 1 billion would be 1 e to the 9. Is that right? You know, what the hell? 1 trillion. 1 teraflop. Flops are floating point operations per second. Right? And there are, that's per second. So 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, and 365.25 days in a year. How many years is this going to end up taking us? Right? That's 4 times 10 to the 10. Right? So what is that, 40 billion years? Right? And that was just just an estimate. Right? So should I sit here and wait? Probably not. Let's kill it. Right? So that illustrates why recursion can be bad. Here's the picture of what's going on. Why is it bad? Here's Fibonacci of 5. Right? How many recursive calls are we going to end up doing? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Right? Let's actually verify that. 5, 15, dead on. Awesome. Right? Good coding skills, right? Pat myself on the back. But what do you notice here? How many times did I call, say, Fibonacci of 2? 1, 2, 3. How many times did I call Fibonacci of 3? 1, 2. How many times did I call Fibonacci of 4 and 5? Let me go in the reverse order there. How many times did I call Fibonacci of 5? 1. How many times did I call Fibonacci of 4? 1. 3, 2. How many? 2 would be, what was it again? 1, 2, 3. All right, 3. How many times did I call Fibonacci of 1? And without even without even counting them up, how many times did I call Fibonacci of 0? 8. The number of recursive calls tracks with the growth of the Fibonacci sequence, because you're basically doing one operation for every single number. Right? It's like adding up 100 numbers by adding 10 plus 20 plus 30 by going 1 plus 2 plus 3 plus 4 plus 5 plus, or 1 plus 1 plus 1 plus 1 10 times, and then doing 1 plus 1 plus 1 20 times, then doing 1 plus 1 plus 1 30 times. Right? There is a lot of repeated computation here. Do you want to do repeated computation? No. You can't do it because it will take what was it, 40 billion years to do so. Right? So what I'm going to do is I'm going to eliminate the recursion. Right? Actually, not entirely eliminate it, but I'm going to do something to eliminate the repeated calculations. Right? So eliminating recursion, you can also use what's called memoization. It is not misspelling. It is not a mispronunciation. It is a weird word invented in computer science. Memoization, not memorization. So here's the basic idea. If you need to compute a value, you pay for the recursion. Right? But each value you compute, you save it in a table. Now, in dynamic programming, which is the larger technique that we're actually talking about here, they call it a tableau, just to be fancier. But we'll just call it a table. Right? In other words, we're going to, i.e., you cache previously computed values. Right? So if you have not computed this value before, OK, fine. I'm going to have to pay for the recursion, and I'm going to have to do it. But if you have computed it before, instead of doing that, now I regret closing that, but instead of computing Fibonacci of 3 yet again for another time, you'll look it up in the table and say, OK, I already computed that value. Here it is. That basically takes that tree that I just showed you, and it cuts off many, many branches. We call that what? Pruning the tree. So that it's not this big, giant, exponentially sized tree. Instead, what happens if you cut a tree all the way, every single branch off that tree? What do you have now? A log or a stick, whatever you want, right? So we're cutting off every single branch in the tree so that we only have to compute the log of the tree. Right? Actually, that's a pretty good pun that I'll use later on when we talk about logarithms. Right? All right. So demonstration. Recompute the Fibonacci sequence using memoization. Right? In other words, we're going to have to build a table. We're going to fill it up with values so that we're not recomputing it every single time. Right? Let me go back over here to my code editor. And I'll call it recursive fib mem for memoization, right? Int n. Right? We might also have to pass in other things here. Okay? What are we going to, well, let's just do that right now. What are we going to have to pass in? I want to know the nth Fibonacci number. I'm also going to have to give you a table, right? I'm going to have to give you an int, long, because we're doing long numbers here. Long table, right? Long table. There's another nice pun. Right? I'm going to give you the table of values. In fact, yeah, let's get rid of that pun. That's a terrible pun. I'll just call it values. Right? These are values that I've already computed. Right? What I'm going to do is I'm going to check that table. If the table already has the value for Fibonacci of n, use it. Right? So if values of n is, what I'll do is I'll use a 0 as my flag variable to say that I've not computed that value yet. Because there are, if you look at the Fibonacci sequence, there are no zeros in it. Right? It starts at 1, 1, 2, and it grows monotonically. Right? So it'll never be 0. 0 is never a valid answer. 0 is never a valid value in this Fibonacci sequence. If you want to, we could do -1 instead. 0 is kind of easier, though. Right? So I'll return, that's my base case now. I will return values sub n. Right? Else, here's where I have to pay for the recursion. Right? I'm going to have to call myself on n-1 and n-2. So what I'm going to do is I'm going to capture that value, though. Recursive Fibonacci memoization, n and values, n-1, and plus recursive Fibonacci of memoization n-2 and values. Right? And I put, instead of immediately returning that like I did up down here, I just returned it. I'm saving that off into a variable. Why? Because if I have paid for the recursion once, I don't want to pay for that recursion again. I need to put it back into my table. values of n is equal to x. Now you can return x. Right? So this is all caching, right? Caching is what? Storage, right? You store things in memory so that you don't have to recompute them every single time. And it's a much more widely used technique other than memoization, right? If you've got an expensive computation that maybe you had to make a network call all the way across the world to Google Earth to get geographical data or something. You don't just ask Google every single time you're connecting to Google Maps or something, and it costs you every time you call Google Maps. You don't do this over and over and over again for the same question. What is the latitude and longitude of Lincoln, Nebraska? What is the latitude and longitude of Lincoln, Nebraska? Right? You don't do this over and over again. You ask it once, and then you store it in memory so that you don't have to recompute it every single time and pay Google every single call. Right? That's pretty good. How do we set ourselves up down here? What does it look like? How does it look different? Well, we're not calling that anymore. We're calling it on n and values. Right? But now we have to set up memory for that table. Right? So set up the table of values. Right? So long star values is equal to long star malloc. Right? Yeah, size of long times. How big should it be? So if I want to compute the 10th Fibonacci number, I would need an index at 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Uh-oh. What about 0, though? So it's going to have to be n plus 1. Right? And make sure that those are in parentheses. Right? Otherwise, is this correct? A long requires 8 bytes. And so you're doing 8 bytes times n plus 1 more byte. Am I going to be able to store that last value? No, I need 7 more bytes. So you need to make sure that you're doing your math correctly here. Right? And even though it's okay when you're doing strings, it's still a bad style to get and a bad habit to get into. Right? Make sure that you're putting parentheses there. Right? You're not paying by the parenthesis. Okay? All right, I've set that up. Now I need to set up your base cases. Right? If there's nothing, like base cases and flag values. Right? So what I'm going to do is I'm just going to go into a traditional for loop here. I0, I is less than or equal to n because it's, or we could go less than n plus 1, I plus plus. I will set everything in there, values of I, to 0, except for the base cases. Values of 0, what was that again? Fibonacci of 0 is 1. Values of 1 is 1. Those are my base cases there. Everything else here is a flag value to indicate that I've not yet computed it. Okay? And what the heck? While we're doing this, let's go ahead and steal this over here and count up the number of recursive calls and print that out as well. Right? Or number of function calls. Let's make sure that this compiles. Oh, wow, cool. All right. Let's do some regression testing. We've changed our program, but not the functionality and not the answers that it should give us. So if we test it with the same values, we should get the same inputs, we should get the same outputs. If I test it with 10 again, I should get 89, right? Yep, 89. But what about the number of recursive calls here? What was it before? 177? We've cut that down to 19. What about, what else did I test? 13. We should get 377 and way fewer calls, right? 13 up here, the number of calls was 753, only 25 now. And now what took 40 billion years takes less than a nanosecond, less than a microsecond, millisecond, whatever, right? Now that might be too large. We might have hit overflow on that, but we can go ahead and test it. What about 50? That looks more reasonable. Right? So let's ask Wolfram Alpha 50th Fibonacci number. Is that right? We're off by, they probably start their Fibonacci numbers at 0, so we're going to be 51. Nope, 49. There we go. And it looks right to me. That number matches that number right there. Right? So they're just off by 1 because they start their indexing at, or they start their sequence at 0. As I said before, sometimes people do it 0, 1, 1, 2, dot, 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 and that's what they did. Right? But I'm probably reaching overflow here. 99th? Maybe not. Maybe I did get it right. Yeah, nope, we're reaching overflow. So even for a 64-bit number, this is too big. Right? But even though we got the wrong answer, we got a quick answer. We got the wrong answer, but at least it was quick. Right? So you're wrong, but at least you got it done quick. All right. So that's memoization, and that's what you're going to be doing on next Thursday, right? So on in hack 12, not tomorrow's hack, but the next Thursday, in hack 12, you'll compute why or how long it would take to compute binomial coefficients recursively, right? And then you'll replace recursive code with memoization code. Right? Now, I just want to make sure, since again these binomial coefficients, I just want to make sure give you a quick introduction to what this means, so that you're not sideswiped by math, right? You got to have some math, right? In fact, many years ago, I took painful efforts to try to get rid of the math in Computer Science 1. And by the first assignment that I did several years ago was I took something from finance, like the loan amortization table or something. I took something from science, half-life, the half-life of radioactive decay, things like that. I took something from sociology or from civil engineering. I took all these different disciplines and I made exercises around them. And I still had a student tell me, this course is all about math. And so we both realized something that day. What is the world? What is every discipline? Math, right? You're not getting away from it, right? So never say, I don't like math. Never say, I can't do math. If you're a living human being that has even lived past the Stone Age, you can do math, right? It's just what level of math do you like doing? Right? Everybody can do it. So what is this math? Well, given n elements, and I'll stop with the LaTeX there. Given n elements, say A, B, C, D, dot, 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 however many you've got, how many ways are there of choosing k of them? Right? In other words, if you do this in terms of sets, how many subsets of size k are there? Right? And this has a well-known correlation to the binomial coefficients. Binomial coefficients are used in binomial distributions, which are they look kind of like normal distributions, statistical distributions, but they're binomial instead. So for example, you know what, let's fire this up and see if we can do this really quick since we have time. Yeah, I'll use this. So we'll do something very, very small here. Yeah, hopefully this works. And switch this over to podium. There we go. All right, as that's starting up. Suppose that I just have 4 elements. And for lack of a better labeling system here, just say that I have A, B, C, and D. Right? These can represent people. I've got 4 people in a class. How many ways are there of forming up a pair of them so that they can go off and do a hack or something like that? Well, what's one way that I can do it? I can go ahead and take A and B and make them a team. I could take A and I could team them up with C. I could take A and team them up with D. I can't form a group I can't go AA because I don't have 2 copies of A, right? If I clone this person, then maybe I would be able to do that. What about BA, though? That's the same group as this group over here, right? So order doesn't matter, right, with combinations. So I've got AB, AC, AD. Right? What other combinations can I form? B and C can be teamed up together. B and D. Right? And then finally, C and D. Right? How many possibilities was that? 3, 4, 5, 6. Right? That corresponds to the binomial distribution, the binomial coefficients. The way that you do this is that n is 4, and we want to form teams of size 2. So now you've probably seen this before if I write it like this. How do you read that? Or maybe you've seen it like this. Or maybe you've seen it like this. Or maybe you've seen it like this, maybe on your TI-82s. I couldn't afford the 89. Right? So lots of different ways of expressing the same thing. Right? How do you read this? The big hint here is C. Choose. Right? It is 4, choose 2 of them. Right? This corresponds to the binomial coefficients. One way of computing this is simply 4 choose 2, or in general, let's keep it general, n choose k is n, what is that thing right there? Factorial times n minus k factorial times k factorial in the denominator. Right? These are rather large numbers. If you go with, say, 40 choose 20, that's huge. How many ways are there of taking, or let's say this class, 200 people choose half of them, right? So 200 choose 100, that's astronomical. That's huge, right? How can we go ahead and compute that, though? Right? One way of computing this is through Pascal's identity. Pretty cool mathematician, well, not a cool mathematician, but pretty cool name. Blaise Pascal. Right? I guess he's as cool as any mathematician can be. Right? So this is Pascal's identity. N choose 2, or n choose k, sorry. You don't have to use a bunch of factorials. Instead, you can use recursion and addition. N minus 1 choose k minus 1 plus n minus 1 choose k. So all you need to do is recurse. Instead of taking one value, like with a Fibonacci sequence, you take n, you take 2 values. Right? So you could write a function called, I don't know, choose n k. Right? And what would it look like? We have to have some base cases here, so I'll go ahead and save those for later. Well, here, how many ways are there of choosing nothing? 1. You don't choose anything. Right? How many ways are there of choosing everything? Also 1. Right? What else is the base case? Yeah, I think those are all the base cases you need, because it's eventually going to get down to 0. Yeah, or this one might lead to this one. So those are the 2 base cases that you need. If you have 2 variables here, what is your table going to look like? Now it's 2-dimensional, right? You're going to run, I don't know, I and j. You're going to run it from 1 up to n and 1 over to k. Not all of it is going to be filled out, but what you're eventually interested in is this guy right down here, n choose k. So you're going to want to fill up this table instead of doing this recursively, because if you do this recursively and you try to compute, say, even 40 choose 20, you're going to be running for several hours at least. If you try to do 200 choose 100, you're going to be running for 40 billion years or so. Right? But what would it look like? Well, if k is 0, or if n is equal to k, you get that second base case here then, return 1. Else, return a recursive call to this function up here, choose, on n minus 1, k minus 1, plus choose n minus 1, k. Right? So it's going to look something like that. For the naive recursion. What you're going to want to do after that is do it with memoization. Create this two-dimensional table, and then fill out the base cases here. There are many base cases. You're going to have to probably use some sort of loop to loop for each value of n. I'm going to set 0 here to all 1s. Right? Along the diagonal, I'm going to set those all diagonal. I'm going to set all of those to 1s. And then I'm going to fill in the rest of this table until I get down to this one. Right? And that is how you can use memoization to do this instead. Right? And that's what you're going to do next Thursday. Again, not tomorrow. Tomorrow is still encapsulation, but this is next Thursday. What we're going to do for the remainder of our time before Thanksgiving is we're going to use this idea in several algorithms. We're going to we're reaching a point now where we've learned a lot of programming. Now let's switch gears a little bit and think more about efficiency, think more about algorithms. And to do that, we need the very basic algorithms in computer science are searching and sorting. Given an array of elements, search through it. Does it contain 0, or does it contain a key? Right? You've all done this before in some sort of exercise, right? Given a string, go through and find all the spaces or something like that. Anybody could do that. But what we're going to do is we're going to start looking at it from not a coding point of view, but from an algorithmic point of view. How efficient is it to search things? Can we make it more efficient? How much more efficient can we make it? And can we sort things? Those two operations are fundamental to all other algorithms. All other algorithms are going to assume, many other algorithms are going to assume that you are given elements in a certain order so that it can process them. Right? We're going to look at it from both a theoretical point of view on how efficient are these things, and we're going to look at it from a practical point of view. Don't write your own. Don't roll your own algorithms. Use what's in the standard libraries. Right? But to do that, we need a bunch of other stuff. We need function pointers. We need comparators. And we're going to put it all together so that we don't have to write our own code. Right? All right. Any questions? Otherwise, that's where we'll be going all the way up until Thanksgiving. All right. Have a good Thursday and then a break, then weekend.